Hi everyone, so we're here and welcome back to GoDevOps. So in the third episode, we opened up a container and explored its internal architecture, so the layers, the runtime, and how it all fits together. And in today's episode, we are taking it one level deeper. So we're going to see how does a container actually runs on a host machine. So we'll trace the full journey from the command you type in your terminal through the runtime and down to the Linux kernel to see how the host makes everything possible. So let's dive in our new episode. So let's start where everything begins. So the command. When you run a container, it looks as simple as typing this command that we see, docker run nginx, in your terminal, but behind the straightforward command lies a multi-stage process happening on the host. So the single line doesn't just start a container, it signals the host to perform a series of actions from pulling the image to setting up the runtime environment and applying security boundaries. So we'll break down how the seemingly simple command kicks off an entire orchestration sequence, starting from the command line and going all the way to the kernel, ensuring the container gets the resources it needs to run. So now that we've seen how the container launch begins with a simple command, let's dive into the next step, which is the container runtime daemon. So whether it's a Docker daemon, so dockerd, or a containerized, this is the core component that listens for your commands and makes everything happen behind the scenes. So when you issue a command like docker run, the daemon steps in and it starts by pulling the image. So if it's not already available, of course, and then begins setting up the environment to run your container. So this includes applying isolation settings like namespace and setting up any required cgroups for resource management and preparing the system for execution. So think of this daemon as the orchestrator that prepares the stage for the containers, which is the actor in this case, can step in and perform. So now let's dive into what happens after the container runtime daemon gets the image name. So first, the host starts by downloading the layers of the container image from a registry. So this is not a single file. It's composed of multiple layers that represent different parts of the container file system. And as each layer is fetched, the host begins reconstructing the container's root file system in a local storage area. So this is the root FS, where the container will live and run. And these layers are mounted together to create the isolated environment we saw earlier. And once this process is complete, the container is ready to execute its application inside this freshly built environment. So now that the image has been pulled and the container's root file system has been prepared, the next step involves setting up isolations for the containers. So the host machine has to ensure that the container is fully isolated from the rest of the system. So this isolation is achieved through Linux namespace and cgroups, which are configured by the host using kernel syscalls. So the clone, the first system call we see here, is responsible for creating new namespace, while the setns call ensures that the container can only see its own environment, preventing it from interfering with the host or other containers. And this step is crucial as it locks down the container's environment and limits its access to only the resources allocated to it. So once the settings are in place, the container is ready for its main process to run securely and independently. So now that the container image has been pulled and the environment has been set up, we arrive at the next key step, which is creating the container process. So this is where runc command comes into play. So once the host has set up the environment, the runtime hands control over to runc, a low-level tool that actually creates the containerized process. So the runc takes care of setting up the process within its own isolated environment, applying the namespace and the cgroups that were configured earlier. So this means that the process will run in complete isolation from the host and other containers, just like a regular process on the system, but with these important boundaries in place. So the runc is the tool that launches the actual process, ensuring it runs securely and independently in its new core. So now that we've prepared the container environment and set up all the necessary isolation, let's talk about the shared brain, which is the host kernel. So all containers on the host share the same Linux kernel, unlike virtual machines which each run on their own full operating system. Containers, in this case, rely on the host kernel to manage things like the system calls, the process scheduling, and the network communication. So the kernel is, in this case, the invisible gatekeeper between containers, enforcing the isolation boundaries we've set up earlier with the namespace and cgroups, and it ensures that the containers behaves as if it's running on its own system while still sharing the same kernel for efficiency. So think of the kernel as the central nervous system of the host, orchestrating communication between the containers while keeping them isolated and independent from each other. So previously we established that containers share the host Linux kernel, but let's now look at how the app running inside a container actually uses that kernel. So unlike a virtual machine that includes its own full operating system, and kernel, of course, a containerized process has no operating system of its own, so it relies entirely on the host kernel to perform low-level tasks. So when the application inside the containers needs to do something like open a file or read from the network or allocate memory, it can't do it on its own. Instead, it uses a system call that we call syscall, which is a direct request to the Linux kernel to perform that task. So these syscalls are the only bridge between a user space and the kernel space. So from inside the container, the process might think it's running on its own system, but under the hood, every time it made a syscall, the call crosses over to the host kernel. So now here's where it gets interesting, is that the host kernel is smart. So it knows this process belongs to a container because of the namespace and the cgroups we configured earlier. So when the kernel receives a syscall from a containerized process, it evaluates it within the context of that container's isolation boundaries. So if we take the mount namespace, okay, we're going to restrict access to its own file system. The network namespace, let it talk only on its own assigned virtual interface. User namespace, we are going to apply container-specific user and group mappings, and the cgroups limits is that we are not going to let it use more CPU or memory than it's allowed. So in short, the containerized app thinks it's making a simple system call, but the kernel is filtering and validating and enforcing rules every step of the way. So this syscall model is the foundation of how containers interact with the system. So one lightweight process isolated by namespace, resource controlled by cgroups, and governed by a single shared kernel that keeps everything secure and separated. So now that we've seen how applications inside containers interact with the kernel through system calls, but when we have multiple containers that are running at the same time, the kernel faces an important challenge: how to share limited resources. fairly and securely. So this is where the kernel scheduler steps in, and this scheduler is the one that decides how CPU time is divided, how memory is allocated, and how input-output requests like disk or network are handled across all containers. And here's the key point. It doesn't do this blindly. So the scheduler always respects the cgroups that were configured when the container was launched. And that means if one container is limited to a certain amount of CPU and a certain amount of memory, the kernel enforces that restriction automatically. And the result is that is of course balance and predictability. So no single container can start the system, and each container gets the resources promised to it, and of course the host remains stable even under the heavy load. So in other words, the kernel is not just executing syscalls, it's also acting like a referee, constantly distributing resources between containers while keeping everything within the boundaries we've set. And now that we've seen how the kernel manages internal resources like CPU, memory, and input-output requests, let's move on to another critical aspect, which is networking. So a container isn't, of course, very useful if it's completely isolated, because it needs a way to communicate both with other containers on the same host and also with the outside world. So this is where the kernel's networking features come into play. So we're going to use the network namespace and the VET pair, so the virtual Ethernet pair. And here's how it works. So each container gets its own virtual machine, virtual network interface, and connected to one end of a VET pair, and the other end is attached to the host bridge, usually something like PR0, or to a network managed by a CNA plugin. And the bridge acts as a gateway. It connects containers to each other and forwards traffic into the host network stack. And from there, the kernel can route packets, applying net rules and enforce security policies. So the result is that each container feels like it has its own independent network card, but in reality, all traffic is carefully orchestrated and isolated by the host kernel and its networking setup. So what should you take away from this video is when you run a container, it's not some little box magically working on its own. It's the host that does all the heavy lifting. So the host receives the launch request, downloads and reconstructs the image file system, configure isolation with namespace and cgroups, and then start the process with the runc. So from there, the host kernel takes over, and it handles every system call, schedule CPU, memory, and input outputs through the scheduler, and ensures networking is properly managed. So in reality, a container only exists because the host is supporting it. So the host is, in this case, the invisible engine that guarantees isolation, security, and performance. And that's the key takeaway. Behind every container, it's really the host that is doing all the work. So thanks so much for watching today's video, and I hope the behind-the-scene role of the host in running containers is much clearer now. So if this video helped, don't forget to like, share it with a teammate, and subscribe so you won't miss what's coming next. And for the next episode, we'll zoom in a key player you've already seen in action, which is the Dockerd daemon. We'll break down what it is, how it works, and why it's essential for managing containers. And of course, if you're curious about something specific, or you have a container concept that feels fuzzy, drop it in the comments, and I really read every single one of them. So yeah, and see you, of course, in the next episode. Goodbye.